Welcome to Project 7, Linux Distribution Build Assistant. Project Overview. Building a custom Linux distribution from scratch is one of the most technically demanding things you can do in the Linux world. You're not just installing packages, you're orchestrating package managers, compilers, live system tools, init systems, and bootloaders into a coherent whole. The knowledge surface is enormous, and the failure modes are brutal. This project tackles that head-on by fine-tuning a specialist model for Animux Genesis 64, a Debian-based live distribution built for animators and VFX professionals. The model learns to guide users through 5 concrete workflows: searching Debian stable repositories, building packages from source when nothing pre-built exists, creating bootable live ISOs with custom branding, diagnosing build failures, and optimizing boot configuration. The results speak for themselves. 91% accuracy on package search queries, 87% success rate on build command generation, 78% of troubleshooting cases resolved without human intervention, and end-to-end project completion 3 times faster than without the. That's not a demo metric. That's a real productivity shift. Here's how we built it. Part 1. Dataset collection. Before we can train anything, we need data, and for a Linux command assistant, data quality matters enormously. A model trained on vague or incorrect commands will confidently generate vague or incorrect commands. So we pull from 3 distinct sources to get both breadth and depth. The first is mecha.org/Linux command dataset, the most comprehensive of the 3, covering a wide range of Linux commands with structured entries. The second is fadi1010/Linux_commands, which fills in general command coverage. The third is hrsvrn/Linux bash commands dataset, which specifically focuses on build sequences, exactly the kind of multi-step workflows. Each dataset is loaded through Hugging Face's datasets library. After loading, we inspect a sample entry from the mecha dataset to confirm the schema, an instruction field, a command field, and an explanation. That 3-part structure, what to do, how to do it, and why, is the backbone of everything that follows. The final print gives you a count per source, so you know exactly what you're working with before any training begins. Public datasets give us general Linux knowledge, but Animux Genesis 64 has workflows that don't exist anywhere on the internet. Creating a base Debian chroot with dbootstrap, initializing a live build workspace with the right architecture flags, configuring systemd services for a VFX environment, none of that is in a generic dataset. This is where domain-specific data creation pays off. We handcraft a list of dictionaries, each containing an instruction, the exact command to run, and a clear explanation of what that command does and why it belongs in the build process. Think of it as writing the world's most precise internal runbook, then converting it into training examples. Once defined, the dataset is serialized to JSON. That format keeps it human-readable for review and easy to load programmatically later. The print statement at the end confirms the count, and that number matters, because you'll see it again when we measure how much this custom data moves the accuracy needle. 3 datasets from different sources plus our handcrafted Animux examples, each with slightly different field names and structures. Before any of this can go into a trainer, it all needs to speak the same language. The convert_to_unified_format function handles exactly that. It inspects each record for known key patterns, instruction command input output, and maps whatever it finds into a consistent 3-field structure. This is the kind of defensive data engineering that saves you hours of debugging later, because schema mismatches are silent until they cause subtle training failures. After conversion, all 4 sources are merged into a single list. The per source counts printed here are your audit trail. If a source contributed far fewer examples than expected, that's your signal to investigate before training. The deduplication step is worth pausing on. Duplicate commands in training data don't just waste compute, they bias the model toward over-representing those commands, which is a form of overfitting. Deduplicating on the command field ensures every example the model sees is genuinely distinct. The final unified dataset is saved to JSON, ready for the training pipeline. Part 2. Multi-stage training. 1D stage training. 1D stage training for the multi-stage training is the architectural decision that separates a mediocre specialist model from a genuinely useful one. Rather than throwing all our data at the model in one pass, we train in deliberate stages, each one building on the last. Stage 1 is broad Linux command knowledge. Stage 2 is distribution-specific workflows. Stage 3 is safety alignment. This mirrors how a human expert actually learns. Foundations first, then specialization, then professional judgment. Stage 1 loads a base model through Unsloth with a 2048 token maximum sequence length and 4-bit quantization. That quantization is what makes training feasible on 24 GB GPUs. It cuts memory footprint dramatically without meaningful accuracy loss. We then apply PFET with LoRa adapters targeting the attention and feed-forward layers, which means we're training a small fraction of the total parameters while the base model's knowledge stays intact. The dataset is loaded from our unified JSON file and formatted as instruction following examples, instruction, command, and explanation joined into a single prompt string. SFT Trainer handles the training loop with a batch size, learning rate, and epoch count tuned for this data volume. When training completes, the model and tokenizer are saved to disk. Stage 1 done, the model now understands Linux commands at a foundational level. Stage 1 gave the model broad Linux literacy. Stage 2 makes it a distribution building specialist. The key operation here is filtering. From the full unified dataset, we extract only the examples containing keywords directly relevant to distribution building, terms like dbootstrap, livebuild, squashfs, initramfs, cheatroot, and similar. The count printed after filtering tells you how much domain-specific signal you actually have. If that number is lower than expected, you'd want to go back and expand the custom dataset before proceeding. The filtered examples are saved separately, then formatted for instruction following in the same structure as stage 1. We load the stage 1 checkpoint as our starting point. This is the crucial part. We are not starting from the base model again. We are building on top of what was already learned. The LoRa adapters from stage 1 are either extended or reinitialized for stage 2, and training runs with the same core hyperparameters. When this stage completes, the model understands not just Linux commands in general, but the specific multi-step workflows that Debian-based distribution building requires. That's the specialization that drives the 87% build command accuracy. Stages 1 and 2 taught the model what to do. Stage 3 teaches it what never to do. This is direct preference optimization, DPO. Instead of learning from correct examples alone, the model learns from pairs of responses, a preferred safe response and a rejected destructive one. The training data here is deliberate and specific. Prompts that could lead to data destruction, partition table corruption, or irreversible system changes are paired with rejections of the dangerous command and safe alternatives that accomplish the legitimate goal. This matters enormously in a build assistant context. A user frustrated by a failed build might ask something that sounds reasonable but maps to a command that wipes their work directory. Without the DPO safety layer, a well-trained model might helpfully comply. With it, the model recognizes the pattern and redirects. The DPO trainer is initialized with the stage 2 checkpoint as its starting point, the preference dataset, and training arguments specifying output directory, batch size, and learning rate. After training, the final model, now carrying all three stages of knowledge, is saved to disk. That 100% safety rejection rate in the evaluation results comes directly from this stage. Part 3. Evaluation. Schon Fischen Evaluation Categories said takes quickly. Training is only half the story. The other half is knowing whether what you trained actually works and being precise about where it works and where it falls short. The evaluation suite covers 5 capability categories that mirror the model's intended use: package searching, source compilation, live system creation, troubleshooting, and safety. Each category gets its own test prompts with expected outputs. The evaluate_response function loads the final model, generates a response for each prompt, and checks that response against the expected content. What you're watching for in the terminal output is the per category pass rate, not just the overall number. A model that scores 95% overall but 60% on troubleshooting is not production ready for a build assistant. Troubleshooting is exactly when users need it most. The per category breakdown is what tells you whether to ship or whether to go back and augment specific parts of the training data. The summary at the end gives you the aggregate accuracy across all categories. Those are the numbers reported in the project results: 91%, 87%, 78%. They came from exactly this evaluation loop. Part 4. Production Deployment. A fine-tuned model that lives only in a Jupyter notebook helps exactly one person. Wrapping it in a fast API service makes it available to every tool in your stack. Build scripts, CI pipelines, terminal UIs, documentation systems, anything that can make an HTTP request. At startup, the fast API application loads the final model through Unslot's fast language model, which applies the inference mode optimizations that cut latency significantly compared to training mode. Two Pydantic models define the contract. Build query accepts a question string and an optional context field. That context is where you'd pass in error logs or build output to get more targeted responses. Build response returns the assistant's answer, any commands to run, warnings if the request touches something potentially destructive, and a confidence score. The /ask endpoint is where the work happens. It assembles the prompt from the query and context, runs generation with temperature and top_p parameters that balance creativity against accuracy, then returns the structured response. The /health endpoint gives your infrastructure a simple liveness check. Start the server with UVCon and you'll see the confirmation message in the terminal. At that point, the model is live and ready to handle requests from whatever calls it. Part 5. Results and Impact. Here are the final benchmark numbers for the deployed model. Package search accuracy came in at 91%, build command generation at 87%, troubleshooting success rate at 78%. The safety layer achieved a 100% rejection rate on destructive command prompts, every single one caught. Average response time is 1.2 seconds, and the model generates an average of 3.4 commands per response, which reflects the multi-step nature of real build workflows. The 100% safety rejection rate is the number worth highlighting. That's not a statistical result. It means the DPO stage worked exactly as designed. No destructive command slipped through in testing. For a tool that will be used during high-stress debugging sessions, that reliability is non-negotiable. The before and after comparison for the Animex Genesis 64 project makes the impact concrete. Before the assistant, 21 build attempts, 19 failures, a 90% failure rate. Root cause analysis took 2 to 3 hours per failure. Documentation searches ran 15 to 20 minutes per issue. Total project time roughly 60 hours spread across 3 weeks. After the assistant, 8 build attempts, 2 failures, a 25% failure rate. Root cause analysis dropped to 15 to 30 minutes because the model suggests targeted fixes rather than leaving you to search blindly. Documentation queries are instant. Total project time roughly 20 hours in 1 week. That's a 3x improvement in project completion speed, not from faster hardware or a bigger team, from a model that encoded the right knowledge and could apply it at the moment it was needed. 5 lessons from this project worth carrying forward. Multi-stage training was essential. The CPT to fine-tuning to DPO progression gave the model domain expertise at the foundation, specialization on top of that, and safety alignment as the final layer. Collapsing those stages into one would have degraded all three. Custom datasets moved the needle more than anything else. The Animux-specific training data improved accuracy by 23 percentage points over the base fine-tune. Generic data gets you most of the way there. Domain-specific data gets you the rest. The DPO safety layer prevented disasters with a 100% catch rate. In a build environment where one wrong command can wipe hours of work, that layer isn't optional. It's the feature that makes the tool trustworthy enough to actually use. Context awareness compounded the value. Passing error logs into the /ask endpoint alongside the question improved fix suggestions by 40%. The model isn't just answering questions, it's reading your specific situation. Next up, Module 8, where we move into production integration patterns and connect everything we've built into a unified pipeline. Before writing a single line of training code, it helps to map the knowledge terrain the model needs to cover. The Linux knowledge base diagram for this project organizes that terrain into 8 domains radiating from a central core. Package management is the entry point for most build tasks. apt, dbootstrap, dpkg, and the dependency resolution logic that underlies all of them. The build system domain covers the compilation toolchains: make, cmakey, autotools, speciverse, and maven. Boot process captures grub, plymouth, ntrms, and the sequence that takes a system from power on to login screen. Service management maps to systemd and the unit files that control what runs and when. Storage and file system, networking, process management, and security and permissions round out the map. Each domain has failure mode specific to distribution building: a misconfigured fstab entry, a missing network interface in the live environment, a systemd unit with the wrong dependencies. Mapping this before training tells you where your dataset needs depth. If one domain is underrepresented in your training data, the model will be weakest exactly there, and that weakness will show up in evaluation. One of the clearest ways to validate a trained model is to watch it generate commands in response to natural language queries and check whether those commands are not just syntactically correct but operationally precise. 4 examples illustrate the range. A query asking for Python files modified in the last 7 days produces a find command with the correct menana and menanapt flags. A query about memory-hungry processes produces a ps command sorted and limited to 10 results. A request for a compressed backup of /etc that excludes log files produces a tar command with the right exclusion flag. Getting that flag wrong would silently include the logs anyway. A request for real-time disk usage monitoring produces a watch command with a 2-second interval. What these examples demonstrate isn't just that the model knows Linux commands. It's that the model understands intent well enough to translate an ambiguous natural language request into a precise, correct command. That precision is what the 91% package search accuracy and 87% build command generation numbers are measuring. Choosing Debian as the base for Animux Genesis 64 wasn't arbitrary. The distribution comparison chart makes the reasoning visible. The chart scores 6 distributions: Ubuntu 22.04, Arch Linux, Fedora 39, Debian 12, OpenSUSE Tumbleweed, and Animex Genesis 64 across 4 dimensions: package freshness, stability, documentation, and wiki support, and hardware support. Debian 12 leads on stability, the most important dimension for a distribution that needs to build reliably across many machines and survive long-running compilation jobs. Ubuntu 22.04 leads on documentation, which matters for a project where the build assistant needs to surface accurate, well-sourced guidance. Arch and Fedora score higher on package freshness and hardware support, but those advantages are less critical when you're building a specialized live system where you control the package selection entirely. Animex Genesis 64's position on the chart reflects its current state, a distribution under active development, not yet leading in any single category, but built on a foundation that prioritizes the stability and documentation depth that a production build assistant requires. The deployment architecture diagram shows what happens between a user asking a question and receiving a verified, actionable answer. The flow starts with the user's question. The first processing step is distribution detection, identifying whether the user is working with Arch, Ubuntu, Animex, or another variant. This matters because the same high-level task can require meaningfully different commands depending on the distribution. Passing the wrong command to the wrong system is worse than passing no command at all. With the distribution identified, the system queries the distro knowledge base to pull relevant context. That context, package names, configuration paths, service names, is combined with the user's question and fed to the Linux-tuned language model. The model generates a candidate response. Here's the step that separates this architecture from a naive chatbot. The recommended command is verified in a sandboxed shell before it reaches the user. That verification step catches commands that are syntactically correct but operationally wrong for the specific distribution or environment. The final output includes both the verified answer and an explanation of why it works, because a user who understands the answer can adapt it when the next problem is slightly different. This verification loop is what makes the troubleshooting success rate meaningful. The model isn't just generating plausible sounding commands, it's generating commands that have been checked.